Hey guys, the objective of this video is to find the ultimate moment hogging, and now we're including the bottom steel. Just before I start, I highly recommend you watch the previous video because I will be assuming a couple things that you already know from the previous video. So, we have this setup here. Now, unlike the previous video, we have compression in our steel and we also have strain in our steel for compression. Okay, so we didn't have this before, we didn't have any strain there, and we didn't have any compression in our bottom steel. But now we have this case. So, for the concrete, it's the exact same case as before. That's why I'm going to skip through it. We do the compression in the concrete, we find alpha 2, we find gamma, and we can find that the compression in the concrete is this formula over here, and we find it to be 5236dn. So including that bottom area of steel is not going to affect the compression in the concrete at all. Alright, so that's why I want you to watch the previous video where I go and explain all this and calculate it. So if you don't understand it, go watch the previous video where I explain all this. And for this case, when we're including the bottom steel, the compression in the concrete won't change. Now, for the steel, once again, we're going to assume that the top steel is at yield because it's at ultimate moment, okay? So this top steel over here, the steel in tension, we're assuming is at yield. And just like before, it's just going to be the yield stress times the area. We did this before, 500 by 2 by pi by 14 squared, because these top bars were N28 bars. Solving that, we'd get 615752 newtons, okay? So the tension in the steel and the compression in the concrete are both unchanged from the previous video. We now just need to include the bottom steel, all right? So what we're going to do is we're going to assume that the bottom steel is still elastic, okay? So we're assuming that this bottom steel over here, it hasn't yielded. And it's a fair enough assumption because most of the work's going to be done by the concrete. So we're going to assume the bottom steel is elastic. That means we need to find the strain in the bottom steel. The way we find the strain in the bottom steel is by doing similar triangles. So by similar triangles, we're going to say that the strain in the steel E subscript S on point 003, so we're doing similar triangles of this big triangle and this smaller triangle bounded by ES. Okay, so that triangle there and the bigger triangle. So ES on point 003 is equal to the distance from there to there, which would be dn minus 47, which is the depth to the layer from the bottom. So that depth over here from there to there is 47. That distance is dn. So that distance from there to there is dn minus 47. So dn minus 47 on the corresponding height for point 003, which is dn. Okay, so we've gone that on that is equal to that on that. Solving this, we get ES is equal to 0.003 dn minus 47 on dn. So just cross multiplying for 0.003. We can then work out the stress. Stress is just elastic, the strain times the elastic modulus. So it's going to be 0.003 times 200,000. So 600 outside of dn minus 47 on dn. Now, the compression in the steel is just the stress times the area. So the stress times the area. We just saw now that the stress is this formula here, so 600 outside of dn minus 47 times by the area of steel. Now the area of bottom steel, we have two N20 bars, so bottom bars with two N20s, so it's going to be 2 by pi by 10 squared would be the total area. So 600 by 2 by pi by 10 squared gives us 376,991 outside of dn minus 47 on dn. Now just like before for pure bending, the sum of the compression equals the sum of the tension. And for our case, we have compression in concrete, compression in steel, and we have tension in the steel. So we know that the compression in the concrete is 5236dn. That was just from here, 5236dn. The compression in the steel we just found here is this formula there. So I've just put that there. And the tension in the steel is 615752. So we saw that here, 615752, because that's at yield, all right? So now what we're going to do is solve this for dn. So we're first going to multiply through by this bottom dn, which would make this dn squared and put a dn there. We would then expand out this bracket there, giving us this formula there. We would then simplify this, putting everything on the left-hand side, giving us this, equaling 0. And then we're going to divide through by 5236 to make it a little bit simpler. So we get dn minus 45.6 dn minus 3384 equals 0. And then we're going to solve for dn, use the quadratic formula. And we'd find that the only appropriate value is dn equals 85.3 millimeters. Okay, so we now know that the depth of our neutral axis from the bottom is 85.3 millimeters. Now there's a couple checks we need to do before we move on. The first check is to see that our assumption that the bottom steel was not at yield is true. So we assumed for the bottom steel that the bottom steel assumed to be elastic, so it hasn't yielded. So we need to show that the bottom steel hasn't yielded. So we know that the yield stress of our steel is 500 MPa. We had 520 bars for bottom, so that's 500 MPa. We can now work out that the stress in the steel was given by this formula here. So we went from strain to stress of our steel, where the stress in the steel was 600 inside of dn minus 47 on dn. So I just rewrote that formula over there. Subbing in for dn, we had dn, we just found now, to be 85.3. So subbing that in and solving this, we would get that the stress in our steel is 269 MPa, which is less than the yield stress, which means that our assumption is correct. So our assumption that the steel in the bottom hadn't yielded, that it was elastic, is true. So we can move on. It's good that we've shown that assumption. The second thing we just need to show is that the sum of the compression equals the sum of the tension, and at the same time we're going to actually be finding the values of compression and tension for each steel and concrete. So we had the compression in the concrete was 5236 dn. So substituting in for dn, which was 85.3, we get that the compression in the concrete is 446,631 newtons. Now the compression in the steel, we reduced down to this formula here before, 376,991 outside of dn minus 47 on dn, so I've just rewritten it there. Subbing in for dn, which was 85.3, and solving that, we'd get 169,270 newtons. And the last thing is just the tension in the steel, we know is just 615,752, so we had that from before, 615,752. Okay, so that's unchanged. And then we can check this, so we can say that the sum of the compression will be the sum of compression in concrete, compression in steel. So that value plus that value, which in kilonewtons is 615.9, and the tension in the steel in kilonewtons is 615.8. Okay, so you can see that they're pretty much the same. There might be a small error just because of rounding errors throughout the calculation, but they're pretty much the exact same. So we can confirm that the compression in the concrete equals the tension. The compression in the concrete and steel is equal to the tension in the steel. So those two equals that one, which is good. The last thing we're going to do then is actually find the moment. Now, we need to find the forces and their lever arms. So we know the forces, we just found them now. Okay, so we know CC, CS, and TS. We just need to know where they act. So we know that for the layers of steel, they're just going to act at their layers, so at 47 and 549. And from the previous video, we said that the compression in the concrete acts at the center of the rectangular stress block. The height of the rectangular stress block is gamma dn. So we need to find gamma dn. So gamma was 0.77, dn is 85.3. So solving this, we'd get 65.7. And because it acts at the center, so that's gamma dn, we need to divide this by 2 to put it at the center. So gamma dn is 32.8. Sorry, gamma dn on 2 is 32.8, so dividing that by 2. We can then draw a nice little picture here, summarizing everything. So I've put on the left-hand side here the compression in the concrete, which we just found previously, is now at 32.8, which is gamma dn on 2. We can then find, okay, so let me just show you. We found the compression in the concrete to be 446,631. 446,631 acts at gamma dn on 2, so 32.8. We know the compression in the steel is 169,270. 169,270 compression in steel. That just acts at the steel layer, at the center of the steel layer, which is at 47. So that's at 47. And the tension in the steel we know is 615,752. 615,752, which just acts at the center of the top steel layer, which is at 549 from the bottom. Okay? So what we're going to do, we can take moments about any point. I'm going to take it about the compression of the steel, just to simplify the process. So the sum of the moment about the compression of the steel, taking anti-clockwise is positive. So you can see this moment is going to be going anti-clockwise about the compression of steel, and the compression of concrete is also going anti-clockwise. Okay, so these moments we need to find the force times the lever arm. So for this one, it's going to be 615752 is the force, the tension in the steel, times by the lever arm, which is the distance from here to here. That distance would be 549 minus 47. Okay, so 549 minus 47. And the next one would be the compression in the concrete, which is 446631 times by its lever arm. Its lever arm would be from there to there, which would be 47 minus 32.8. Okay, and they're both positive because they're both going anti-clockwise about our point of interest. And solving this, we would get a moment of 315.4 kilonewton meters. Okay, and just to show you from the previous video, when you didn't include the bottom steel, we had 310.2. Now we've got 315.4. So it's increased the moment capacity a bit, but not too much, okay? Now this point is very important. It's not really that relevant now, but when we come to beam design, which is a later topic, I want you to remember that when you include when you don't include and include, the moment capacity is quite similar, okay? Which is going to be a vital assumption when we get to beam design later on in the course. Anyway guys, hope that helps, and we'll see you in the next video.